There's antimony, arsenic, aluminum, selenium, and hydrogen.
Hi, I'm Mrs. Hoover, and today we're going to talk about the alkali metals. Now, we've been talking about reactivity in class, and if you recall, as you move from the stair step, where the division is between the metals and the non-metals up in the corner, reactivity increases as you move down towards FR. So today we're going to look at 3 metals specifically in group 1A, which is called the alkali metals. The 3 that we're going to look at is lithium, which is close to the top, right under hydrogen, and then we're going to look at sodium, and then we're going to look at potassium, which is the 3rd one down. So you might be able to guess already which one is going to be the more reactive, but we're going to check it out. So the first one we're going to look at is lithium, and these are stored in a solution of oil because it's very reactive with water. Now that said, we are going to throw it into some water to see what happens here. This is a chunk of lithium. I'm going to cut it so that you guys can see what it looks like once it's cut. So as we cut into the lithium, this is kind of hard to cut into. I would say harder than it would be to cut through something like a carrot. It's a little harder than that. But the neat thing is, do you see how it's a dull gray on the outside? Once you cut it, it's a shiny silver gray on the inside. So this is lithium, again, top of the alkali metals, underneath hydrogen. Before I add it to the water, I'm going to add a special chemical called phenolphthalein to it. Phenolphthalein is an indicator, and I'm not sure if you've heard of an indicator before, perhaps in middle school, but an indicator is something that would change color in the presence of an acid or a base. In the case of phenolphthalein, if it comes in contact with a base, it will turn a bright pink color. So I'm going to add a couple drops to our beaker of just plain water. And as you can see, the water stays clear because it's neutral. It is not an acid or a base. So now we're going to add our lithium to the water that has been treated with the phenolphthalein. You can see already the water starting to turn pink, so that indicates that a base is present. If you look closely, there's bubbles forming as well. 2 indications of a chemical change are color change and then bubbles released. So there's definitely a color change here. So I think we can confirm lithium is reactive with water. It gives off a gas, and it is producing some sort of base during this reaction. Okay, the next metal that we're going to look at from the alkali metals, group 1A, is sodium. And again, it's stored in oil because there's water in the air, and if it was exposed to air, it could react with the water in the air. So I'm going to grab a chunk out of here, and I am going to cut it up so you can see. On the outside, it looks like a chalky white, but when you go to cut it, you will again see that it's nice and silvery inside, and this time it's easier to cut. It's kind of like a clay that you might have used when you were a little kid. So if you can see, I'm going to cut it again. Look at how nice and silvery that is on the inside. So you can see, it makes sense that they're in the same family, that we have lithium and sodium in the same family. It is a softer metal. I'm able to cut through it with a knife. It's soft and silvery, and let's see if it reacts with water. So now I'm going to take our chunk of sodium, and I'm going to add it to our water with phenolphthalein in it. Much more reactive than the lithium. Much more reactive than the lithium in that. In that, there was fire and a very loud sound. That was the production of hydrogen gas, and that actually ignited whenever we had the sodium was reacting so readily. The hydrogen gas ignited and created that loud sound. As we can see, the alkali metals have proven to us to be very reactive. The first metal that we did was lithium. It is highest up on the periodic table, and it was reactive. It gave off a gas, it fizzed around, definitely produced a pink color with the phenolphthalein, so it is a base. Then we did sodium. Sodium was a lot more reactive than lithium. Instantly, when it hit the water, it caught on fire. The hydrogen gas that built up actually ignited, and some of the water came out of the beaker, and the phenolphthalein turned a very bright pink because a base was formed. Actually, sodium hydroxide was formed when we added sodium to water. For our grand finale here, we are going to use potassium. Now, potassium is an old nemesis of mine, and it's the farthest down on the periodic table that we are going to look at for the alkali metals. And in my first year of teaching, a chunk of potassium popped out of the very same beaker that we are looking at. Well, maybe not the very same beaker, but a beaker just like it when I was doing this demonstration, and landed on my skin, which contains water. And so the potassium reacted very readily with the water in my skin and left me with a reminder that potassium is very reactive. So let's try this in the beaker. I'm going to take a cut of a chunk of potassium, and I think you'll see some similarities between potassium and sodium and lithium, just in the way it looks. So again, you can see this alkali metal, potassium, is also a dull gray color. When we cut into it, it's definitely very silvery on the inside. And of the three alkali metals we've looked at, it's the softest of all three. It's almost the consistency of Play-Doh. So it's nice and silvery on the inside, and here's the perfect size chunk that we are going to throw into our water with the phenolphthalein in it. For what hopefully is obvious reasons, we're adding a much smaller piece of potassium than we did of sodium and lithium. So I'm going to throw this in here and back away. So that was a teeny tiny piece of potassium. Imagine if I would have used a chunk the size that I used for lithium or sodium. Definitely much more reactive than either one of those. So that should confirm our trend of reactivity increases as we move down the periodic table towards Fr. So those are our alkali metals. We started with lithium at the top of the alkali metals. Then we went to sodium, which is just below lithium. And then finally we ended up with potassium. There are a couple more in the alkali metals that we're not able to do, of course, in our lab because they do get more reactive as we move closer to Fr. So we'll stick with potassium. No more scars, no more injuries this year. So we'll just wrap it up with that.